Okay, can everybody see my screen?
Yes.
Okay. All right. So we're going to do section 8.5, which is probability. It's just an application of integration. Um, one of the nice things about looking at probability is it's one of those things that we see all the time, but we just don't really understand a lot of times where it comes from and how it works. So we're going to look into a little bit more of how they actually figure out exactly what the probability of something happening is. So probability is looking at a continuous random variables, and you typically see this. Let me say this. This is where what you'll typically see is a nice little bell curve shape. That's a normal distribution of values. And when we're looking at probability, we want to determine what the actual value is under the curve from a specific amount to another specific amount. So if you've done any kind of statistics or basic statistics before, you'll know that the bell curve is based on the mean and then the standard deviation. And your standard deviation, one standard deviation will occur at 67% of the values. No, you don't need to write all this down. It's not going to be in the problems. Two standard deviations will be 95, and three standard deviations will be 99.7. In a stats class, that's what you get taught, and you use that to determine a lot of different calculations and information. However, calculus allows us to actually come up with the exact values of that information, and that's what we're going to look at tonight. So instead of just using a standard values for it, we can come up with the exact value for any breakdown of the points, which is quite nice to do without having to actually use tables and all this other stuff to figure it out. So let's go back a few slides. So let's say we want to know the probability that blood cholesterol levels is greater than 250. So we look at, or the probability of height of adults is between 60 and 70 inches. So females and males have different heights. That'll look a little bit differently there. Or the probability that a battery you're buying lasts at least 100 to 200 hours. Or my favorite is that toaster you're buying is going to last you more than 2 years. If you've ever bought an item at a store, you'll notice they give you a limited manufacturer warranty, and it's a specific number of years. And if you ever have the bad luck or normal luck, basically right after your warranty ends is when something is going to happen with that item. That's because they've done all the calculations and determined that is when the item is most likely to start failing. So they give you the warranty just before that point. So they actually do these calculations to figure out exactly when those things are going to fail and then give you your warranty just a little less so they don't have to pay out or make you buy the extended warranties. So every one of them has what's known as a probability density function. That's going to change based on what we're looking at. So we have the normal distribution, which we're going to look at a little bit later, but every item has a probability density function. And that means between two values, we can do the integral of that function to determine how much space is underneath that curve, which is all we really do in integration anyway. Since it's a probability density function, everything under that curve from negative infinity to infinity has to equal 1. Because if I add up all the values under it, I would get 1 out, which or 100% depending on how you want to think about it. So this is one curve. We looked at that before. That's the nice little bell curve piece. So this function, from negative infinity to infinity of that function, has to equal 1. If it doesn't, then it is not a probability density function. So that's going to be our first test to make sure that the function we're looking at is an actual probability density function. Once we've proved that it is, we can then use it to figure out what the probability is between a couple different points. All right, so let's look at a situation. So let's see if I have this. They don't give me the nice curve in the book. So they're going to give me this function. They said let f of x equals 0.006x, parentheses x minus 10, and that's from 0 to 10. Anything outside of that, f of x equals 0. So anything below 0, f of x equals 0. Anything more than 10, it equals 0. So the first thing I have to do is I have to verify that this is a probability function, density function. Remember, there's only one criteria that I need to know, that the integral from negative infinity to infinity equals 1. As long as that probability works, or that rule works, I know this is a probability density function. So we plug it in. Now, this one I know is 0 for anything other than 0 to 10. So I don't need to look from negative infinity to infinity. I can just look at it from 0 to 10, because I know all the rest of them don't really matter. So we do our integration for this one. This one's a simple integration. We can pull out the constant, multiply through the x through. So I'm just doing the integral of 10x minus x squared, which gives me 5x squared minus 1/3 x to the third. We plug in 0 and 10. The 0 cancels everything out. The 10 is going to give me 500 and 1,000 over 3. So 0.006 times 500 minus 1,000 over 3 is exactly 1. So this is a probability density function. Now that I know it's a probability density function, I can now do a calculation on it. So the other thing they wanted us to look at was they wanted us to know what's the values between 4 and 8. So you're going to do the exact same thing, except my integration is now just going to be between 4 and 8. So the nice thing is, since we already did the integral, we know what the integral comes out to be, so I don't have to do it again. We're just going to plug in 4 and 8 into the problem. When we plug in 4 and 8 into the problem, we get 0.544. So the probability that this value is going to be between 4 and 8 is about 54.4%. Now we look at it, it's like, okay, that's just a random example, not really useful when we're looking at some real life situations. So let's actually look at a little bit of a different one. So wait times and equipment failures and stuff like that are typically modeled by exponential decreasing probability density functions. So we're going to look at an exponential function, a decreasing exponential function. So my decreasing exponential function I'm going to use is f of t equals a e to the negative ct. So that's the function I'm going to use. I don't know what a and c is yet. A and c are going to be just constants right now. So I'm also going to have to add in, because we'll have to look from negative infinity to positive infinity. So I want to look at this, since we're going to be dealing with like wait times and equipment failures and stuff like that. Time less than 0 doesn't make much sense. So we're going to expand this function out just a little bit. We're going to say it's 0 when t is less than 0. And then it's that function when t is greater than or equal to 0. All right. So everybody understand why that's a decreasing exponential function? The negative sign there makes it a decreasing function.
Yeah.
So, all right. So now we've got to figure out what a. Well, let's figure out what a is. We'll figure out that piece first. So I know that if this is a probability distribution function, that the integral of it has to equal 1. So I can do my integration. And since I only really have to worry about I know less than 0 is going to be 0. I only have to worry about from 0 to infinity of this one. So I'm going to do a e to the negative ct dt, and that has to equal 1. So let's do the integration and plug in the numbers and see what the value is for a that's going to give me 1. So if I do the integral, so the a can come out because that's a constant. And then I have e to the negative c t dt. So to do this integration, we have, we could just do a simple u substitution. Remember, c is still a constant, so I don't have to worry necessarily, I don't have to worry about that as a variable. So that c is going to come out in front. So my integration is a, and then it's negative 1 over c, e to the negative ct, and that's evaluated from 0 to infinity. Now, when we can't do a function by plugging in infinity to it, so when you're doing this, we do what's known as a limit. So we're looking at the limit as x goes to infinity. I'm going to put the a back in so I don't have to keep writing it outside. And we're doing it from 0 to x. So we're looking at that limit as x goes to infinity, not necessarily right at infinity, because things don't exist at infinity, but that limit does. So when we plug in that limit as x goes to infinity and the 0, this ends up coming out to be just a over c. Because when I plug in 0 for the t, I get 1 because it's e to the first power. And then when I get the when I plug in the infinity part up there, it just goes negative c to the x because that's going to infinity. Now, when I'm subtracting that off as an exponential function, if it's decreasing, as it's going to infinity, what's it getting closer and closer to? It's getting closer and closer to 0. So this function ends up being just a over c, and then it's 1 minus 0, so it's just the a over c. So that's why I get the a over c when I plug in the infinity and the 0. That part makes sense? Yes, no?
Yeah, I think I get what you're saying.
All right.
What did you say you did at the top when you took the integral?
Well, so on this one, you just do the u substitution. I'm making u equal negative ct. And that's why I get the negative 1 over c in front.
Okay.
All right, so the goal was to figure out what a was. So remember, the very beginning of this whole thing, I said that problem, whatever I was going to do, equals 1. So I know a over c equals 1. So if a over c equals 1, then a has to equal c. So if a equals c, my function that I'm going to have at the end, the exponential density function, which will work for any and every exponential density function, because we did this as a generic form, not a specific form. So I've got 0 when t is less than 0, and I've got c e to the negative ct when t is greater than or equal to 0. So that right there is a exponential density function that we're going to use to do quite a bit of problems in a minute. And we're going to figure out what C is in a few minutes as well. So actually, if you look. So this is what the function looks like when we're looking at it going out. So as time increases, it's getting closer and closer to 0, and more of the probability is going up that whatever's happening is going to get done. So if it's a wait time on a phone call, the probability that you're going to get answered is higher. If it's the probability that something's going to fail, it's getting higher the further and further we go out. All right. Average values. So now this is where that wait times and stuff comes into play. Suppose we're waiting for a company to answer phone call. So if you ever call up the post office or basically any business in the world now, you're probably going to be waiting on hold. How long would you expect to wait on hold before you hung up? That's what a company has to figure out. So, because they know that if they have you on hold longer than that value, you're going to hang up and they're going to lose business or they're going to have upset customers. So they have to hire more customer service agents to keep that number down below a specific amount. And that's what they're looking at. So we're going to let that density function curve that we just created a minute ago actually work for this because it's still an exponential, a decreasing exponential curve. So they're assuming in the problem that we're going to do that the company doesn't have anybody on hold for more than 60 minutes. I know for a fact I've been on hold for over 3 hours for the post office. So that doesn't hold true. I was really mad at the post office. That's why I didn't hang up. So when we're looking at the average curve, we're actually going to do the same thing. We're going to basically split it up. We're looking for the average of every single point to figure that piece out. So we're going to go a little bit further. So the function that I'm going to have is it's t times f of t. So in this case, my equation for this problem is from 0 to 60, t f of t. Now, we need to figure out what that f of t piece comes into play. So that's my symbol for m, for mean, is the u, or mu. We've seen that before when we were doing, you've probably seen that before when you're doing mean in a lot of different places. Or if you did any kind of standard deviation, stuff like that, or probability before, you've seen that symbol before. So the mean is the integral from negative infinity to infinity of x f of x, just like we were doing with the functions before. So that's going to give me my mean of whatever function I have. So this is my average function. Notice it's basically the same as the function we just did before, except there's an x in front of it. So nothing really changed in that point, because that's going to give me my mean of my probability. So let's look back at that problem that we just created. So here's my exponential distribution that we just came up with a minute ago. And we want to find out, in this case, what C is so that we can, or what the value is, and then we could actually use that to do a little more, make it a little more useful for us going forward. Because we're not going to know what C is, but a lot of times we will know what the mean is. So my mean is going to be t times c e to the negative ct. So remember, it's just t times f of t. So let's do this integral. So we have to do this one by integration by parts because I have multiplication in this case. So we're going to make u as t, and we're going to make dv as c e to the negative ct. So du is dt, and then v is negative e to the negative ct. Because the c's end up canceling each other out. So I plug in, I do my integration by parts. So it's the uv. So I get negative t e to the negative ct. And the integral of v du. So that's that. Which that comes out to be the 1 over c minus e to the negative cx over c when I do that integration. As x goes to infinity, this piece right there and that part right there goes to 1. So, and when I plug in the 0, the only thing that's, well, in this case, if you plug in 0, that's going to disappear. These aren't going to work. So when you plug in the infinity and everything else out, we end up getting 1 over c as my answer. That makes sense? You'll see why we did it in 1 second. Now that I know that my mean is 1 over c, I can replace that c in my function with mean, which is something that I will know when we're doing our work. So instead of having a random variable like we did in the problem with c, or when we had a in the original problem, we wanted to get rid of that. So now I've got a value that I actually will know from my problems. I've got the mean in there. So it's mean to the negative 1 equals e negative t over the mean. So I now have a better probability density function that'll allow me to use this to find some values of information, which is what we're going to do now. Not in this slide, though. All right. So let's use what we just found. So I have my density function as f of t and then my have 1 over u or mu e to the negative t over. For that's t is greater than or equal to 0. So that's my probability distribution function. So in this problem, it says, suppose that the average waiting time for a customer's call to be answered by a company representative is 5 minutes. So for this problem, we could ignore the top one because it's 0. So for this problem, my f of t is going to be 1 over 5, which is 0.2, e to the negative t over 5, when t is greater than or equal to 0. Any questions on where we came up with that? Or are we good with that?
I think it makes sense.
Now that we got this as a probability distribution function, we know that it works, and we have the equation for this specific problem. We can now use it to determine what's the probability that things happen. So in this problem, we've got two situations. They want to know where the call is just during the first minute and waits more than 5 minutes. So let's use our problem to do the first one. So remember, my function is 0.2 e to the negative t over 5. And we're going to do t. So we're going to do the integral from 0 to 1 for this problem, because we want to figure out for the first minute. So 0.2 e to the negative t over 5 dt.
I don't see any of your writing.
Oh, I forgot to switch screens. There we go. I switched screen on my wrong screen. Thank you. So we're just doing 0 to 1 in this one. So notice I'm not using the t f of t because we're not looking for the average value. We already found it. We're just looking for the probability, which is just the integral of that function. So the integral for this, when we do it out, we get 0.2 times negative 5 e to the negative t over 5. And we're evaluating that from 0 to 1. So when we plug in 1 to this, we get, so 0.2 times negative 5 is negative 1. And we plug in 1 to that, we get e to the negative 1/5. And when we plug in 0, this becomes 1. So I get minus a negative 1. So I get 1 minus e to the negative 1/5. Which, if we plug that into a calculator, gives me approximately 0.1813, or 18.13%. So there's an 18% chance that your call would be answered in the first minute from this customer service place if their average wait time is 5 minutes. The next part of this problem said, let's see if it's above 5 minutes. So we're going to do the same thing. We're going to do the integral, but we're doing it from 5 to infinity this time. Nice thing is I already did the integration. So I don't have to worry about that part. I know that the integral is that. So it's the limit as x goes to infinity of negative 1 e to the negative t over 5 from 5 to infinity. So if I plug in 5 to this, I get negative 1, or, well, let's plug the infinity in first, because we plug in the bigger one first. If I plug infinity to this, that's going to come out to be 0, because as x goes to infinity, this piece goes to 0. So that part goes to 0. So therefore, negative 1 times 0 is 0. And then if I plug in 5 to this, I get negative e to the negative first power. So the answer is e 1 over e is my answer to this, which is approximately 0.368, or 36.8% of the people wait longer than 5 minutes, or more than 5 minutes. All right, so here's a question for you. I said the mean was 5 minutes, right? So why would less than half the people wait more than 5 minutes? What do you think?
Because they've already been answered.
Well, if the mean, if I have 100 people sitting on hold, right? Mean is in the middle, right? So you'd think about half the people would answer before 5 minutes and half would be answered after 5 minutes. That makes sense, right?
Yes.
So that actually, if you think about it in that way, which is the way I just proposed it, that's median, not mean. Because, so when you're looking at mean, if I have somebody that's on hold for an hour, even if I had 5 people on hold for 1 minute, and I had 1 person on hold for an hour, I would take that 65 minutes worth of time and divide it by 6. So it actually ends up being about, what, 11 minutes approximately for each person would be the mean. So because you can have some people that are on hold for a very long time, it kind of it stretches it out towards that other side. So, or you have a bunch of people answer early, that could pull it the other direction. So that's why it's not exactly a 50-50 split. So mean is nice, but it's not always 50-50. That's why when you're looking at the next thing we're going to look at is when we look at the normal distribution. A normal distribution curve states that the mean and the median are identical, that there's an equal number of values on either side to balance it out. So that's how all the rest of your probability works with the normal distribution. All right. Let's look at a normal distribution curve. So your normal distribution curve is this wonderful little equation right here. Now, it looks really, really complicated. However, a lot of that information we're going to have to know to create the curve. So you'll see one extra symbol in this problem that we haven't looked at before, and that's the little O symbol. That's known as sigma, or the lowercase sigma, and that stands for standard deviation. So when you create a normal distribution curve, we need to know our mean, and we need to know our standard deviation, because that tells you how spread the data is. So we're going to have we would have all that information when we're plugging it in. So this fraction up here becomes a lot simpler to deal with. So as my standard deviation gets bigger, my curve flattens out. So you can see here that's a standard deviation of 2, a standard deviation of 1, and a standard deviation of 1/2. So as the standard deviation gets smaller and smaller, it's more compressed towards the mean, which means more values are closer to the mean. As the standard deviation gets higher, it becomes more spread out. So the factor that's in front is what we use to actually make it equal 1. So remember when we did the, back when we first figured out that A value for the exponential decay probability distribution, or decreasing exponential function, we had to figure out A to make it work so that it came out to be 1. In this case, when they solved this problem to make it equal 1, that was what they got. It was 1 over standard deviation times the square root of 2 pi. So that's the value that's going to make this probability function work and give you the value of 1. So that's right there. All right, so let's look at the wonderful IQ table. Has anybody ever actually taken an IQ test?
No.
No.
So there's lots of IQ tests out there. You can take them online and stuff like that. Most of them are not very accurate. If you ever get a chance to take one, though, they actually do. It's a whole like series of tests that you actually have to go through and do. They figure out what your IQ is at. It's the interesting thing, though, is that over time, your IQ has changed. We're smarter today than people were 200 years ago. So our IQ as a species is higher today than it was 200 years ago. However, the IQ score of every test is 100. So what they do is they constantly readjust it so that the average is 100. So if you took an IQ test from 100 or 150 years ago, you would score way higher on it today than they did back then because we've grown in intelligence over time. So IQ tests don't change over time. Just like SAT scores, actually, they do the same similar to that thing too. So if you took an SAT test a long time ago, you say, oh, I got a score of 1300. And somebody says today, oh, I got a score of 1300. That value means two different things. And knowing a lot about the SATs, it actually means the opposite of the IQ test. SAT scores are going down. So if you scored 1300 on the SATs, say 20 years ago, that's a lot better than a 1300 on the SATs today. All right, so we want to find the percentage of population that has an IQ score between 85 and 115. So we know our mean is 100, and they're giving me my standard deviation as 15. So in essence, we're looking for one standard deviation around the curve. Now, one standard deviation based on the rules should be about 68%. So we plug in the values. We're doing from 85 to 115. We plug in all this wonderful information here. And when we simplify this all down, we end up getting a function, and they didn't actually do it. Oh yeah, they did it right there. We end up getting the function as e to the negative x squared, which we can't actually take the derivative of, or the integral of. So we have to actually use a calculator to do this. And actually, I think because there's a couple situations where you have to actually do this. And I don't know. Nope.
So you could literally just type in like e to the negative x to the 2 to the squared just on the calculator, and it should calculate it for you just like that, a normal graphing.
No. That's actually what I was going to show you. So it doesn't do that, unfortunately. So you actually have to use a calculator that does integrations. And yeah, there we go. So we're doing this one from, where did they do it from? So you actually can plug it in. This will actually, yeah, I have a thing there. So you actually can plug into this. It'll actually do the calculations out for you. I wanted to see if Desmos did it, and it didn't do it. but you actually have to use an actual calculator that does the integrations to figure it out. If you have the TI 89s, they'll do it. I think some of the newer Texas Instruments might also do it. They have the integration function in there. As long as you have the integral symbol that you can type in, you can actually type in the actual values and it will give you the answer. So you could actually type this whole thing right into your calculator and it should give you the answer as long as you have the integral symbol in there. So as long as you have that symbol that you could type in your calculator, it should give it to you. It just won't do the integration value for you, give you as a function, but it will give you an actual value. So it is something to try on your calculator to make sure that it works, because it does definitely help you on some of these problems, especially ones that you can't actually integrate. And I think somebody asked me a question from section 8.1 or 8.2 this week that it had a function. It was 1 plus the cosine. It was the square root of 1 plus cosine squared x. And you can't simplify that down, so you actually just had to plug that in the calculator and get the answer as well. So when you do that, you actually do get something as it should come out to be about 0.68, which is the rule. It's 68% of the values are between 1 standard deviation away. The next one on this one said anything over 140% or 140 scores. So we plug in 140 in the infinity. Now, again, we can't do this one out and actually do the integration, so we're going to have to use a calculator to figure this part out as well. And I really wish Desmos actually did an integral, but they don't. Oh, it does. I take that back. I found it. To do an integral on Desmos, you just type in integral, and it gives you the values there. So they're going to use 200 for this one. And it actually doesn't matter. You can use technically any number. You just don't want to use infinity. So I could actually put 500 there. It wouldn't actually matter much. So then we're going to do 1 over 15 square root 2 pi. E. And dx. And apparently it doesn't like what I typed in. All right, I'll have to play with this a little more. That should work. It did. All right. I don't know why it's not letting me do it. I will have to play with it a little more to figure out exactly how to type this in. But apparently Desmos actually does do it. I just have to make sure I type it in correctly. When you plug this one in, you'll get 0.0038. So about 4% of the population has a IQ of greater than 140. For reference, Einstein's IQ is 160. And apparently the smartest guy on Earth right now, his IQ is 208. So. All right. And that's it for probability and using the functions. So. This.